At first glance, the strength of a material should be, well, just that, a property of the material itself. Steel is strong, glass is brittle, and gold is soft. You can look it up on a chart: tensile strength, yield strength, hardness, all fixed numbers. But when you shrink materials down to the nanoscale, something remarkable and paradoxical happens. They get stronger, much stronger. In fact, nanostructured materials can exhibit mechanical strengths approaching their theoretical limits, far beyond what bulk versions of the same material can achieve. This puzzling phenomenon is known as the size-dependent strength paradox. Let's take a step back. In classical material science, we expect larger samples of a material to behave predictably, but in practice, larger materials often fail far below their theoretical strength. Why? Because of defects, dislocations, grain boundaries, microcracks, and voids. These imperfections act as weak points, places where stress concentrates and fracture begins. The bigger the material, the higher the chance it contains a critical flaw. This is why, for example, a perfect silicon crystal might withstand extreme pressures, while a large silicon wafer can snap from much less force. But now zoom in-way to nanostructured materials, nanowires, nanopillars, thin films, or nanocrystalline metals. As the size of these structures approaches a few tens of nanometers, something profound changes. The density of defects decreases, or they're removed entirely. Explocations, the main carriers of plastic deformation, become confined, unable to move freely or even form. Grain boundaries may shift from being weak points to barriers that block dislocation motion, strengthening the material. This leads to a stunning result: smaller is stronger. Take gold, for instance. In bulk, gold is famously soft and malleable. You can dent it with a fingernail, but fabricate a gold nanowire just 20 nanometers thick, and it can withstand stresses several times higher than steel. Or consider nanocrystalline nickel, whose grain sizes are less than 100 mm. It can exhibit yield strengths double or triple that of its coarse-grained counterpart. These observations don't just challenge our intuition, they upend conventional design rules. You might ask, but shouldn't these scaling effects be predictable? Why do they seem to contradict bulk theory? Here lies the heart of the paradox. Classical mechanics, including continuum elasticity and plasticity, assumes a homogeneous material full of statistically distributed defects. But nanoscale materials often have too few defects for these statistical models to hold. Instead of behaving like a material, the structure starts behaving like a system with discrete atomic behaviors. Dislocations may not be able to form, or if they do, they might be pinned, blocked, or annihilated at surfaces. In essence, the material is too small to fail the way big materials do. And surfaces matter a lot. At the nanoscale, the surface-to-volume ratio becomes enormous, and surfaces are often more ordered, strained, or chemically distinct than the bulk. This can lead to surface hardening effects, especially in materials with strong surface reconstructions or oxide layers. Combined with size effects, the result is a suppression of plasticity and an increase in hardness and strength. Interestingly, the size-dependent strength paradox has been experimentally confirmed across a wide range of materials. Nanopillars of copper and nickel showing strengths near their ideal shear strength. Silicon nanowires surviving bending tests that would fracture bulk silicon. Graphene, a 2D sheet of carbon atoms exhibiting record-breaking intrinsic strength, ~130 GPa, despite its atomic thinness. Yet this increased strength often comes at a cost. Many nanoscale materials are strong but brittle. They can resist enormous stress but then fail catastrophically with little warning. In bulk, materials can absorb and redistribute stress via dislocation motion or plastic deformation. At the nanoscale, with dislocations suppressed, there's no escape valve for stress. So what does this paradox mean for applications? In nanomechanics, it opens the door to ultra-strong, ultra-light components, tiny springs, sensors, resonators, and actuators. In composite materials, embedding nanoscale reinforcements like carbon nanotubes or nanocrystalline grains can dramatically improve performance. In electronics, Nanostructured metals can be used as interconnects that resist deformation, even under thermal cycling. And in biomedicine, nanoscale needles, stents, or scaffolds benefit from enhanced strength without bulky geometry. But there's also a challenge. Designing at the nanoscale means rethinking the assumptions of traditional materials science. Engineers must consider how defect dynamics, surface energies, grain orientations, and dimensionality all interact to create properties that are nonlinear, non-intuitive, and often spectacular. And perhaps that's the deeper insight of the size-dependent strength paradox, that strength isn't just about what a material is, it's about how it's structured and how big it is. At the nanoscale, materials transcend their classical identities. Gold becomes stronger than steel. Silicon bends, crystalline perfection becomes attainable. In the end, this paradox doesn't just challenge our models, it invites us to reimagine the limits of what materials can do by designing from the atom up, because sometimes when it comes to strength, less is truly more. The size-dependent strength paradox refers to the counterintuitive phenomenon where materials, when reduced to the nanoscale, exhibit mechanical strengths that far exceed predictions based on their bulk properties. As classical continuum mechanics suggests, strength is an intrinsic material constant. However, as the characteristic size shrinks, especially below the micrometer or nanometer scale, materials begin to approach their theoretical strength limits. Nanowires made of gold or copper, for instance, can exhibit strengths approaching their ideal theoretical limits, sometimes more than an order of magnitude higher than their macroscopic counterparts. Much like breaking a large chocolate bar with ease, while a tiny fragment of the same material is nearly unbreakable due solely to its small size. At small scales, mechanical strength is not merely a bulk average property, but a dynamic outcome influenced by defects, dislocation motion, and surface effects. In bulk materials, strength is governed by the initiation and propagation of dislocations, grain boundary sliding, and defect accumulation. However, in nanoscale structures, such mechanisms are suppressed or absent, leading to significant enhancements in yield strength, fracture toughness, and elastic modulus. For example, nanopilers fabricated via focused ion beam milling exhibit higher yield strengths with smaller diameters, a trend that is reminiscent of a tightrope that holds more weight the shorter it becomes, where less slack means less room for failure and greater strength per unit. The enhancement in strength at the nanoscale arises from mechanisms such as dislocation starvation, surface-dominated mechanics, constrained plasticity, and limited defect nucleation. In extremely small volumes, dislocations cannot multiply or propagate easily, resulting in what is known as dislocation exhaustion or source-limited deformation, and the increased surface-to-volume ratio amplifies the influence of surface energy, pushing the material closer to its ideal strength. Metallic glass nanowires, for example, can exhibit high tensile strengths because their deformation occurs through shear banding without the usual dislocation mechanisms to relieve stress, similar to a pristine crystal without cracks, where pressure builds relentlessly, making the material appear unnaturally strong. This paradox also highlights the complexity of materials' behavior across different scales, underscoring the breakdown of continuum assumptions at the nanoscale where new rules of behavior emerge. The interplay between structure, scale, and intrinsic material dynamics means that mechanical properties are not absolute but result from complex interactions. Nanolattices created via 3D nanoprinting, for instance, exhibit high stiffness and strength-to-weight ratios due to their hierarchical architecture and nanoscale elements, much like a beehive constructed from silk threads whose strength is derived not only from the material itself, but from the precision and scale of its construction. At the nanoscale, the energy landscape for deformation and failure is dramatically altered, with fewer dislocations and limited defect accumulation, resulting in higher energy barriers to plastic flow. Energy that would otherwise be absorbed by defect motion is instead stored elastically, or released catastrophically upon fracture. In nanocrystalline metals, for example, the traditional Hall-Petch relationship breaks down at very small grain sizes because grain boundary sliding becomes dominant, changing energy dissipation pathways in a manner akin to snapping a cold spaghetti stick that stores energy until a sudden, clean break occurs. Size-dependent strengthening also introduces new dimensions in the informational landscape of material science, where mechanical performance is encoded in geometric, structural, and compositional parameters. Atomistic simulations of nanocrystalline alloys demonstrate that by statistically manipulating grain boundary character, it is possible to optimize strength, toughness, and fatigue resistance, effectively programming the material's behavior, much like writing a message in invisible ink that only reveals its full impact under the right nanoscale conditions. Biological systems routinely exploit size-dependent mechanics for functionality, as seen in the nanoscale fibrils in spider silk or the mineralized nanostructures in seashells and bones, where hierarchical design combines strength with flexibility. The enamel in human teeth, for example, achieves remarkable hardness due to its nanoscale structure of aligned apatite nanorods that resist deformation through confinement, analogous to a suit of armor made of feathers, where each tiny component is weak alone, but together creates a protective shell far stronger than expected. Despite the remarkable potential of nanoscale materials, significant challenges remain in scaling up these properties for real-world applications. Nanocomposites, for instance, may lose their strength advantages if nanoscale reinforcements are unevenly dispersed or if weak interfaces develop during processing, which is much like trying to build a skyscraper out of diamonds. The individual building blocks may be the strongest available, but connecting them without introducing weak spots is a formidable challenge. The future of materials engineering lies in exploiting the size-strength paradox through innovations in bottom-up fabrication, nanomanufacturing, and machine learning guided design. Emerging research in metamaterials and architected nanolattices shows that by carefully tuning geometry and scale, it is possible to achieve theoretical strength limits in practical components, much like constructing superstructures with Lego blocks made of steel arranged with nanometer precision, thereby creating materials that are faster, lighter, and more functional than those produced by traditional methods.